Hey guys, hello everyone. Welcome to this session and welcome to the Rasayan Academy. So basically guys, in this particular video, we are going to be talking about another important aspect of organometallic chemistry, and this is something which is taking most of the part of organometallics. That is the metal carbonyls. Alright, so we are going to understand how many different types of metal carbonyls are there and how can we classify them and what are the important characteristics physically and chemically of the metal carbonyls that we have to study for the exam. Okay, so let's move onwards, and first let's understand that how many different types of metal carbonyls are present. Okay, so first of all we have a mononuclear metal carbonyl. Mononuclear matlab ki you are having one metal atom, one metal center, and that is surrounded by the carbonyl in different geometries. So first example we'll see, when we are talking about a tetrahedral geometry, it has to be the nickel tetracarbonyl. Alright, example, you must have all seen this organometallic compound a lot of times. It is nickel tetracarbonyl, it is tetrahedral in nature. Then there is palladium tetracarbonyl, again tetrahedral in nature. Why it has to be tetrahedral sp3? Because it is the metal is there in the zero oxidation state. All the d orbitals are fulfilled, and that's why it cannot be square planar. It has to be a tetrahedral system. Then we move onwards to a pentagonal bipyramidal system. We see that for the iron group, iron, ruthenium, osmium, all of this. Alright, so we say this for the iron, FeCO whole 5. Again, it is a 18 electron species. For all of its group members, it is going to be trigonal bipyramidal system. All right. And yeah, when we move down, actually what happens is there is a higher chance that when we move down the group, there is a high chance that the trigonal bipyramidal changes to square pyramidal. Why? Because square pyramidal is such a geometry which is only supported by very big metals. All right, so it is also possible that when you are going down the group, iron is supporting trigonal bipyramidal. However, osmium may support square pyramidal in the same coordination number. All right, so yeah, then we move onwards to octahedral system, where you are having vanadium, chromium, molybdenum, and tungsten. All right, all of these are going to be the octahedral complex. All right, for example, you have seen this very often. CrCO whole 6 is octahedral, follows the 18 electron rule as well. All right, so yeah, next one is a binuclear carbonyl. What do I mean by that? I'm having two fused nuclei, मतलब कि इसको mononuclear को हमने fuse कर दिया है. Alright, by removing some of the common carbonyls, that will give us binuclear carbonyl. Now, how many different types are possible? That will be dependent on the electrons, electron count. जैसे कि ये देखो, here when we are talking about a cobalt one, cobalt can only dimerize in this way, CO2 CO whole 8. Why? It can only have one metal metal bond, nothing else. One metal metal bond. Now there is one more thing it can do. In the solution phase, all the carbonyls are going to be free, but in the solid state, these carbonyl may end up becoming a bridging carbonyl. Why? Because the structure is a little bit more rigid. All right, and why not in the solution? In the solution, the structure is a little bit more free, free to move around like that. Okay, but the electron count remains the same as I told you. One carbonyl will always give 2 electrons. Okay? Chalo, as long as it is bonding from the carbon side. So yeah, 2 electron donor over here and 2 electron donor over here as well. आगे चलते हैं. Fe2CO9. So this system remains like this. It has one Fe bond. Here there are 3 bridged carbonyls, and there are going to be 6 terminal carbonyls. Just remember the structure, alright, because there are few structures which are worth remembering. Okay, then we move onwards to another type where we are having one metal metal bond and 5 carbonyl per metal. That happens in manganese, technetium, rhenium, the same manganese group. You have seen this very often, Mn2CO whole 10. Whenever it is reacting, it is going to break the metal-metal bond and react with some other species. ये हमेशा question में पूछा जाता है. Okay, so yeah. So these are some of the examples. आगे चलते हैं polynuclear में. Now polynuclear can have like 3, 4, more than 4, more than 2 actually. So polynuclear में I'm taking few examples, and to simplify I've taken like the carbonyl as a dot. ठीक है, इससे आपको क्या होगा, मेटल के ऊपर फोकस होगा सिर्फ. Fe3CO whole 2 whole 12. So here you see this Fe3CO whole 12 has 3 metal-metal bond, and just by the 18 electron rule, if you want to find out, you will just get this simple skeleton. Alright, क्योंकि ये अभी भी LNCC है, lower nuclearity carbonyl cluster ही है. So you're going to get this thing, and you will say that there will be like 4 carbonyls with each iron, because that is going to sum up to like 12. So by theory you can only say this, but by the IR spectroscopy you can say that there are 1 and 2 bridging carbonyls present in this molecule. Alright, so yes, this is how the structure going to be. Now we move onwards to the other ones, of the other congeners of the same group. See, as I told you, iron is the smallest and it has a higher tendency of doing the bridging. जैसे जैसे ग्रुप में नीचे जाते हैं, going down the group or in any group, going down in any group, the metal disfavors carbonyl bridging as the metal size increases. Alright, so as we go down the group, the metal size increases, and that's why the carbonyl being bridged is not so possible. For ruthenium and osmium, it's going to be free. Per metal, 4 carbonyl, very simple. ठीक है, अब हम आगे चलते हैं. When we see these examples, ये क्या है? These are 9 electron species. Iron and ruthenium and osmium, these were all 8 electron species. हम आगे चलते हैं on the 9 electron species, and we are taking M4, that is a tetranuclear cluster. So M4, CO, you have seen this example, CO4, CO whole 12. Yes, we have seen this in the isolobal analogy also. It can be broken down into 4 CO whole 3 pieces, and all of them connected together in the form of a tetrahedron system. Yes, but again, since the cobalt is smaller, so all the 3D metals are going to favor the carbonyl being bridged. Alright, that's why how many, see, you have to remember this in this stage, that there was a question in CSIRNET once जिसमें पूछा गया था how many bridging and how many non-bridging carbonyl are present. So you see that there are 3 bridging, total are 12, right? 3 bridging carbonyl, 1, 2 and 3, and 9 terminal carbonyl are present, both for cobalt and rhodium. Now don't think that just like ruthenium, rhodium is also not doing the bridging. Here rhodium is doing bridging, and here ruthenium is not doing bridging. So be very very careful. Okay, ऐसा नहीं है कि 3D, 4D, 5D सब same ही होंगे in all the groups. So here only iridium does not show the bridging. However, rhodium shows. इसके एग्जाम्पल देखते हैं. यहाँ पे ये देखो, when we were talking about this iron tricarbonyl complex, there were 2 carbonyls which are bridging. See, this one at the back and this one at the front. Okay, ruthenium nobody was bridging, osmium nobody was bridging. So these 2 are same structures. However, look at this. Cobalt has how many bridging carbonyls? 1, 2 and 3 bridging carbonyl. Iridium does not have any bridging carbonyl, and rhodium structure is going to be the same as cobalt. not as iridium. Okay, so there is a difference, just remember that. Now guys, before we move onwards, because we want to understand the characteristic properties of metal carbonyls, so we need to understand about the carbonyl ligand first, and then we will see how it is going to behave when it combines with different metals under different environments. Okay, तो ये देखो, a carbonyl has electron density, non-bonded electron pair density on the carbon, because of which it can work as a donor to a metal. ठीक है, no problem. But also it is found to be accepting electron on the carbon itself. मतलब कि क्या है, ये sigma donor है, donating sigma electrons, forming a sigma bond. It is a pi acceptor, forming a pi bond, but all it does that through carbon atom. Through carbon atom only. Oxygen is not getting involved in directly into bond formation. ठीक है, तो ये सब काम कार्बन का कार्बन ही कर रहा है. So how is it happening? We have to understand the molecular orbital diagram for that. ठीक है, तो ये देखो. Now, you already know carbon has 2s2, 2p2 electronic configuration very well. Oxygen has 2s2, 2p4 electronic configuration. So 2s and C, I have like taken a combined diagram over here. You can just, simply, if you don't want to take the combined diagram, you can just add the 2s first. You get 2s bonding sigma 2s and you get sigma 2s star, just like that. And then you can take the 2p and 2p and then you form the bonding and the anti-bonding. But I have not done that. I've taken a combined diagram because this is the corrected diagram for the carbonyl. Why? Let's see. Kyunki it's not always about bonding or anti-bonding in carbonyl. It's about bonding, non-bonding and then anti-bonding. Got it? So you see, we must be able to describe what is bonding, what is non-bonding, which is being able to, the orbital which is non-bonding is donating electron to metal. ठीक है? Then comes the anti-bonding. तो चलो, 2s को और 2p में कार्बन में डिफरेंस काफी कम है. As compared to oxygen, the energy difference is much higher. There's a mixing happens. All right. So what happens is we will consider the combined effect. There is 1 2s and 3 2p, total 4 orbitals. Here also 1 2s and 4 2p, total 4 orbitals. 4 plus 4 gives you 8 orbitals. So draw it like this. Sigma, this is 1 sigma. This is 2 sigma because this is still stable. All right, this 2 sigma is mostly coming from the 2s, but still it is stable. Then comes the pi, then comes the 3 sigma, and then finally comes the 4 sigma. Now out of which, अच्छा ये भी है यहाँ पे, out of which these two are the most anti-bonding. These two are the most anti-bonding. These are the most bonding. These are the most bonding out of all of this, and this has a non-bonded character. This has a non-bonding character. Even though if you are showing it like this, it is still having the non-bonding character. It can be donated very easily. So you have how many electrons? You have 4 and 6. You have 10 electrons. So 2 in the most sigma, then comes the 2 sigma where 2 more electrons are being put, then comes the pi. All right, 4 electrons are being put, and then lastly 3 sigma, the next 2 electrons are being put. So these 2 electrons which are donated to the metal are the ones which are present in the 3 sigma over here, which has a non-bonding character, and where it is accepting the electrons in the 2 pi. We also call it pi star because this is the most anti-bonding. So it is accepting from the metal into the pi star orbital. And that also requires some geometry consideration. The sigma bond forms through a sigma bonding orbital, and the pi back bonding takes place from the metal d orbitals. Okay, so we are going to also look into that. But ये आपका carbonyl का molecular orbital structure था. It is a sigma donor from a non-bonding, partial non-bonding, partial anti-bonding character orbital. and accepts the electron into the pi star orbital, which is the most antibonding, one of the most antibonding. Okay, so this is how a carbonyl works as a donor and acceptor. अब हम आते हैं metal and carbonyl के bond formation में. So metal carbonyl complexes, they are very popular for having the pi acceptor ligand or the pi acidity. All right. So when we describe the bonding of a carbonyl to a metal, we have to understand how the sigma bonding and the pi bonding are taking place. Alright, so for example, when you are considering the sigma bond, we have to consider the sigma bond to the metal from the carbonyl first, and then comes the pi bond. Alright, like this. So first the base skeleton forms because of the sigma bond. So how the sigma bond is forming, the lone pair on the carbon is donating into the sigma orbitals of the metal. Who are the sigma orbitals of the metal? Definitely the d orbitals which are present on the axis. So either it could be a dx square minus y square, or it could be a dz square. Alright, any one of these orbitals, these are present on the axis, and maximum times what we see is, if we consider the dz orbital of the metal, all right, let's say we are considering the dz orbital of the metal, dz square, all right, that is binding to the carbonyl in this way. Okay, so this forms the sigma bond over here. Now what happens next is, if there are any orbitals which are present in between the axes which have the z component, for example, we have definitely got the z component. We have discussed this before already. Let's say we are talking about dxz or dyz. Now they are going to have the z component in common, and they are going to form a bond with a similar symmetry orbital, that is the sigma or the pi star, sorry, that is going to be the pi star. So this is how the pi star is going to be, plus minus minus plus, like that, and this is how the d orbital is also going to be for the metal. So same symmetry orbital, like this, pi back donation takes place from the metal to the carbonyl. Alright, that's why the arrow direction is like this. Okay, from the metal d pi orbital into the carbonyl pi star orbital. Okay, so this is how the bonding interaction of metal and carbonyl will take place. Okay. Now what happens is, a carbonyl or actually a metal carbonyl bond is very sensitive. Alright, and based on all the ligands which are surrounding it, it's going to be behaving differently. Like we can have the change in environment of the metal, a change in the ligands can cause a direct effect on the stretching frequency of the carbonyl. Okay, so we are going to see some factors that how the carbonyl stretching frequency is going to change. पहले थोड़ा सा हम नाम देख लेते हैं, nomenclature देख लेते हैं, and then we directly move onwards to the IR stretching bands of the carbonyl. ठीक है. So first thing we talk about metal carbonyl. So we have already seen how many different types of metal carbonyl are present. कुछ common name ऐसे हैं कि nickel tetracarbonyl. This is a common name that we have been calling this. But the actual name or the IUPAC name is tetracarbonyl nickel, because you know that first the ligands are going to be written, and then we write the metal, and then we write the oxidation state. Now, while naming coordination complexes, we used to use the stock notation. Bracket में हम Roman numbers में लिखते थे. ठीक है, तो यहाँ पे भी हम वही use करेंगे. Stock notation we are going to use. However, since nickel is zero oxidation state, we write 0. Okay, then we come over here. Alright, for example, this is the same pentacarbonyl iron 0, same. Here we are talking about, see, the complex is there in this side, in the cationic side. It's a cationic complex. So it is going to be hexacarbonyl manganese 1 chloride in this way. Very simple. So it is basically the same as doing the nomenclature of simple or complex compounds. Okay. चलो आगे चलते हैं. We do one more simple nomenclature or classification that you must have understood by now. When we are having complete carbonyl in a complex, all the ligands are carbonyls. Example, these that we have discussed right now. These are known as homoleptic metal carbonyls, that all the ligands are going to be carbonyl. And if there are some other substituents which are present, like a proton, like let's say chloride, phosphine, many different combinations, then it will be known as a heteroleptic metal carbonyl. Okay, just basic classification, nothing else. अब हम चलेंगे IR frequency में. See, we are going to talk about all the important spectroscopic parts, the IR spectrum, the proton NMR spectrum, the 31 phosphorus NMR, all these important things. So let's talk about the structure. So when we are talking about the carbonyl stretching frequency, we need some comparison, right? We need some comparison when the carbonyl is free, when it is terminal, when it is bridging, and when it is bonded to metal, when it is bonded to a positive metal or a negative metal, all those things we are going to compare. So जो free carbonyl होता है guys, a free carbonyl, this shares the maximum stretching frequency for a carbonyl, that is 2143. Now you have to remember this value 2143. क्या ये maximum है? इससे ऊपर नहीं जाता है? Definitely जाता है. You see over here, when we are having a free carbonyl, it is 2143 like this. Okay, but when we are having a CO positive, we have removed one electron, and definitely it has a positive charge, so the frequency is going to increase like this. Also, sometimes it is mentioned that when a boron is binding, just like it is donating to a metal, it can also donate to a boron like this, isn't it? So when it is donating to a boron, boron has no possibility of giving it back, just like a transition metal. So it can only accept. That's why the stretching frequency also is higher than a free carbonyl. Okay, just remember this. It is very important. अब हम इसको छोड़ेंगे यहीं पे, वापस जाएंगे अपने टेबल पे. Okay, because we need to see the modes of binding. So a free carbonyl is 2143. A terminal carbonyl, that is, gives 2 electrons to the metal. Terminal carbonyl is going to be 1850 to 2120 के बीच में. Okay, it is very important that we remember this range because it is not a fixed value. It could be 1850, it could be 1950, it could be 1920, anything like that, and that's why we have to remember the range. Then symmetric mu2 carbonyl bridge. So whenever you are doing a bridging, you will write this term mu. How many number of metal it is bridged to? Obviously bridging होगा तो दो तो होंगे कम से कम. So it is going to start from mu2. So mu2 you can write when there are 2 metals. When there are 3 metals, you can write mu3 carbonyl. Alright. So what happens is when 2 metals are bound to carbonyl, symmetric means same metals. Then what happens is, this is a sigma bond, no problem. This is also a sigma bond, and there is a metal-metal bond in between. Now these sigma bonds are actually this carbonyl carbon is giving one electron to each of the metal. It's not giving 4 electron, only one electron. लेकिन जो ये metal वापस देता है pi back bonding के through, based on the pi back bonding, the carbonyl bond order decreases, and that is why the carbonyl stretching frequency also decreases. So what happens is, when the carbonyl is getting back from the metal like this, then what will happen? Metal carbon bond is going to become stronger, but the carbon oxygen bond is going to become weaker. So this bond becomes stronger. इसकी अगर कोई frequency पूछे तो ये strong हो जाएगा. But this frequency is usually asked, so this is going to be weaker. Alright, and that happens all the times. Okay, so when this metal is coordinating to this carbonyl, there are two metals giving back the higher amount of electron density to carbonyls. That's why the frequency is going to decrease. 1700 से कितना आया? 1860. So yeah, going down from this 1850 से going down. Then we see symmetric mu3 carbonyl. Definitely this is going to even be lesser because the bond order has been decreasing. अब 3 metal है तो तीनों metal donate कर रहे हैं. So the bond order is very less. Look at this carbonyl. It's like a C single bond O. So 1600 से लेकर 1700, this is the stretching frequency for a mu3 bridged carbonyl. Okay, now we are going to move onwards and we see some factors which affect the frequencies of metal carbonyl. As I told you, the carbonyls are very sensitive to the environment that they are present in. So let's say I'm talking about a metal carbonyl where the metal is actually having a positive charge. पूरे complex पे positive है. Complex पे positive मतलब metal is positive because carbon is a neutral ligand. Okay, so that metal which is positive is going to only take electrons from carbonyl. It is only electron deficient. It will not be able to give back. However, यहाँ पे लिख देते हैं हम poor pi back bonding. Okay, अगर हमने ले लिया neutral, let's say I am taking a neutral metal, then this is going to be good at pi back bonding. Why? Because it is neutral, it does not have charge, the metal, that's why it can give. ठीक है, ये जीरो ऑक्सीडेशन स्टेट में है. लेकिन अगर मेरे पास एक नेगेटिव चार्ज आ जाए पूरे कॉम्प्लेक्स के ऊपर, yes, that means that the metal is very good at pi back bonding. All right, and when there is 2 minus, then this is going to be having a very low stretching frequency of carbonyl because this is very good at pi back bonding. All right, just a simple concept. You increase the electron density on the metal, it is going to give to the carbonyl कि मुझे burden नहीं लेना है, तुम लो burden. All right, because it has a pi acceptor ability, that's why. So the order of increasing carbonyl bond strength, if you see that bond order is directly proportional to bond strength, all right, that is inversely proportional to, or let's say bond order high होता है तो stretching frequency भी high होती है, so it is directly proportional to the stretching frequency like this, and this is inversely proportional to the bond length, just in case if the bond length is asked in any further question like this. So how are we going to answer this question? Who is going to have the maximum carbonyl stretching frequency? The maximum will be 1 where you are having a positive charge in this way. Then comes the neutral one, then comes the having 1 minus charge, and then comes having iron having 2 minus charge. So ये हो गया इसका correct sequence. And what is the factor that affected the metal carbonyl stretching frequency? That is the charge on the metal. Alright guys, so now let's look at the other factor which may also determine the carbonyl stretching frequency. तो मैंने आपको बोला था कि that the carbonyl, the metal carbonyl bond, this is very sensitive with respect to all the other ligands which are connected to the metal. So when we are saying we are having a homoleptic complex of the carbonyl, that means all of the ligands are going to be carbonyl only. That means all of the carbonyls are pi acceptor, so all of these are going to have like similar bond lengths and bond order with the metal, okay, because they are all showing the same similar behavior, same behavior. But if we are putting some other ligand which is, let's say, phosphine across the carbonyl, this is just trans 2 carbonyl, then what is going to happen? You know that the phosphines are very strong sigma donor. If these are very strong sigma donors, then the metal is strongly going to do the pi back donation into the carbonyl, and because of that, the carbonyl bond order is going to decrease and the bond length of the carbon oxygen bond increases. Alright, however, the bond length of the metal and the carbon bond decreases, alright, because of the pi back bonding. So this is the question is just asking you the correct order of carbonyl stretching frequency for these compounds over here is going in the IR spectrum is going to be. So take your time and then try to answer it, okay. So as we know, if we just first compare that what is going to be the electron donating property of phosphine, we are going to have a separate session on phosphines where we are going to see that phosphines have a very variety of donor properties, and because of that, some are strong donors, some are weak donors. Not all phosphine are going to form a strong bond with the metal. ठीक है, तो यहाँ देखते हैं when we talk about PME3, this is a very strong sigma donor because it's only donating, it's not a pi acceptor. PCl3 has chlorine, which is electronegative atom attached to phosphorus, that is not allowing it to like donate the electron. So ये क्या हो गया? Poor sigma donor. Then there is oxygen, even poor sigma donor. And finally this one, this is only a sigma donor, not pi acceptor. However, some of the properties like phosphorus has a vacant d orbital. So if there are electron withdrawing groups connected onto phosphorus like these, they can still be working as a pi acceptor. Okay, sigma donor and pi acceptor. So what is going to be the stretching frequency? The strongest donor is going to have the weakest stretching frequency. All right. So we have already made a table over here. You can see. See, what I have done is I have compared those phosphine ligands which are most frequently used for bonding: PF3, PCl3, POMe3, PPH3, NCCH3, that is your acetonitrile, and pyridine. And you can also take ammonia or NMe3, so on and so forth. These are most commonly asked in the examination. So we are doing a comparison of the facial isomer. Okay. We are doing a comparison of the facial isomer. Why the facial isomer? Because if you see in the facial isomer, if you will see, then the metal has, you know, two different types of ligands, L, L, L. These are going to be exactly opposite to the carbonyl. That's why the facial isomer. So in the facial isomer, what is the direct effect of this ligand on the carbonyl stretching frequency? If the ligand is a poor sigma donor like PF3 is a poor sigma donor, then the frequency is going to be high like this. Then again, ये थोड़ा सा strong sigma donor as compared to PF3, so a little bit lower frequency. Then this is still a better sigma donor, so still lower. Which is the best sigma donor? See, along with the in the phosphine, PPH3 is the best sigma donor. That's why it is having the lowest carbonyl stretching frequency, because it is giving to the metal which gives to the carbonyl, so lowest. फिर हम आगे चलते हैं एसेटोनाइट्राइल के लिए, even better donor because it is going to be mostly donating and not like very less accepting. Pyridine, again the nitrogen lone pair can only do one thing, it can be only donated. All right, it is not involved into resonance. So yes, again a strong sigma donor, so 1888 or least frequency this is going to be. All right, so when you are having phosphines, there is a variety of carbonyl stretching frequencies based on the donorability of the phosphine. ठीक है, तो यहाँ पे अगर हम बात करते हैं पाई एक्सेप्टेंस की, so you see nitrosyl has the best pi acceptance, even better than carbonyl. Then comes PF3, then your alkyne, then PCl3, then phosphide, then trialkyl phosphine, and then these. All right, so it is very important. Just take care of the donor atom over here. Carbon is a strong donor atom as compared to the nitrogen. Okay, so yeah, all of these are very, very important. Just keep this in mind for future if any kind of question like this is being asked. So the correct answer of the previous question is going to be in this way. PCl3, NMe3 is going to have the lowest frequency right over here because it is the strongest donor. Then comes this, because this is also strong donor. This is a poor donor and a better acceptor, and PCl3 is again a poor donor and a better acceptor. All right, so this is going to have the maximum stretching frequency. और अगर bond order पूछ लिया तो let's say the same question is asking you metal carbon bond order. Let's say this one. Then what will happen? What is going to be the series? Just the opposite. Because ये जो पूछ रहा है ना carbonyl stretching frequency, they are asking you about the carbonyl bond order. Definitely carbonyl bond order is the strongest in this one क्योंकि यहाँ पे least pi back bonding है. Okay, so if they are asking you about the metal carbon bond order, then the series is going to be reversed. Okay, now we move onwards and we talk about some more examples which have been given in the book. All right, I have referred a lot of books for making these lectures. B.D. Gupta, Miss Larentar, Rasayan Atkins, you can go through these books as well. Okay, now there are some frequencies which are important for us to go through. Metal carbonyl stretching frequency for various complexes. As I told you before that CO plus has the maximum stretching frequency as compared to free carbonyl as compared to this one both. लेकिन आपको ये भी पता है that when the carbonyl is free it is 2143 fine, but when it is connected to BH3 it has some positive property, so the value increases and CO ये तो खुद ही positive है तो obviously increase होगा. लेकिन we still have one higher chance of getting a greater carbonyl stretching frequency, that is copper CO whole plus, and there's a plus charge over here. So this is a tetrahedral system and it is having a plus charge over here. So 2202, such a high stretching frequency, even higher than the free carbonyl or this one, all of these. ठीक है, तो ये बहुत important है, इसको ध्यान में रखना. Then we move onwards, we see that अब ये neutral हो गया है, it is neutral now, so 2057, okay. Now there's a negative charge, value decreases. 2 negative, even decreases further. 3 negative, बहुत ही कम value हो गया है. 4 negative, even decreases further. So what is happening? ये हो गया charge effect. This is charge effect. That when you are having more charge on the metal, it gives more to the carbonyl, and that's why the bond order and the frequency decreases. Now when we are talking about these complexes, see you again, जहाँ पे भी cationic complex होता है ना guys, the value is much higher as compared to a free carbonyl. Okay, so this is iron hexacarbonyl 2 plus once again, and the value is very high for the carbonyl 2204. Then comes this plus, this is 2098. Then comes a neutral one, okay, decreases, negative आया, फिर से decrease. So all of these are what? Charge effects. ये सारे के सारे क्या है? Charge effects है. Okay, so you just have to remember. Now let's move onwards to a question. A metal complex having an empirical formula FeC9H7O3Cl has one ligand as substituted cyclopentadienyl group. It is an ionic compound and has poor solubility in hydrocarbon solvent. The compound gives a white precipitate on treatment with AgNO3 solution. Assuming that it obeys 18 electron rule, suggest the structure. Now, why are we doing this kind of a question? Exam में तो MCQ आता है ना? But yes, it has been like if you see the previous year questions and if you see the back questions of BD Gupta, there are a lot of questions which are framed from that book. Okay, so that's why it is important कि हम MCQ पे ना जाएं, हमें जो अच्छे question मिल रहे हैं वो practice करें. ठीक है? So try figuring this out. These are the most interesting questions of organometallic chemistry, finding out the structure. Yes, तो ये empirical formula है. In this way, it has one ligand as a cyclopentadienyl group, but that also substituted. अब कैसे substituted है, that I don't know. So there is a CP, but there is some kind of a substitution X, let's say I'm writing. Even it is an ionic compound. Ionic compound मतलब charge है N plus. Okay, and has poor solubility in hydrocarbon solvent. So it is ionic, has a N plus charge. Compound gives white precipitate on treatment with AgNO3 solution, which means कि बाहर कौन है? Cl minus. Right, the Cl minus has to be outside. How many chlorine are there? Just one. So the charge should be just one, isn't it? Yeah. Assuming it follows 18 electron rule. अब ये कैसे find out करेंगे हम 18 electron rule? We'll just take the iron. How much do we have? We have C5H5. यहाँ से minus करो C4H2. What does that mean? And there are O3. That means that there may be 3 carbonyls like this and there is a CH2. Then absolutely it is going to be C4H2O3. Isn't it? 3 carbonyl और एक methylene group हो गया. तो क्या करेगा इस? हम ये कर सकते हैं that we put 2 of the carbonyls over here and we have a CH2. So we can't just write CH3 over here. We have to write CH2CO in this way, maybe. Yeah, we have to write it like this. या फिर हम एक काम कर सकते हैं. We can also write this structure over here because there is one very important thing. There's a CH2 group that I can add to this molecule. So what I can do is, and then I'm writing a CH3. So what are the hydrogens in total? 3, 4, 5, 6 and 7. Still there are only 7 hydrogens. So it is the same thing. So what next I'm going to check is whether it is a 18 electron species or not. So 5 plus iron 8 plus 3 into 2 6 minus 1 absolutely 18 electron system. तो ये जो structure होगा इस complex का, it is going to be like this. Alright, it's a very interesting way to understand these kind of questions and you must all try this. So now we move onwards and we do one more question. The IR spectrum of this particular complex eta 5 CpFeCO whole twice at room temperature gave 3 bands 2005, 1961, 1795 centimeter inverse, and at high temperature gave 3 bands at these values, alright, which are actually lesser than these values. Alright, also the carbonyl stretching bands for eta 5 CpOS CO2 whole 2 gave us 3 bands at these frequencies at both the room temperature as well as the higher temperature after heating. So what can you infer from here? Like what is the conclusion that you find out from this information? So guys, there are 4 options. Just try this question on your own and after that I'll answer. So the complex is eta 5 Cp, which is connected to iron. Along with that, 2 of the carbonyls per iron. So all of this is connected to iron. Okay, this is the Cp eta 5, right? So it gave us 3 bands. Why is it giving us 3 bands? There are 2 possibilities. That is, if at lower temperature and higher temperature it's becoming different. You see that these two are like almost similar, only a difference of 10 centimeter inverse. These two are also very similar, only a difference of like 10-12 centimeter like that. But this one, the third value has changed drastically. Alright, it's like a 200 centimeter inverse change. So why is this changing? Because we can expect when there is iron involved, iron is a small 3D transition element, so we can expect this kind of a possibility that maybe there is a carbonyl which is bridging. Alright, maybe there are 2 carbonyls because totally there will be 4 carbonyls, so maybe we can say that there are 2 carbonyls which are bridging like this. So if they are bridging, they are going to have a different value as compared to this and this. Alright, it's going to have a lower value, the value of a bridging carbonyl. Okay, and when you're heating this, then what will happen? The bonds, the bridge bonds are going to open up like this and it is going to become free. Let's say the molecule now is right like this, where all of the carbonyls are converted to terminal carbonyls. All of these are terminal carbonyls now. Now this difference is only observed when we are checking for iron. This difference is not observed for osmium because I've already told you that when we move down the group, bridging of carbonyl with metal is difficult because the metal size increases. That's why. So bridging carbonyl in osmium complexes only. This is wrong. Bridging carbonyl in both complexes is wrong. Only the carbonyl is bridging in the iron complex. So C is the correct answer. No bridging carbonyl, again wrong. So A, B and wrong, C is correct, D is again wrong. Alright. Again, now guys, we are going to move onwards and understand a very important thing about the spectrum of different geometries of the metal carbonyls, right? So metal carbonyls, as you have already seen, nickel tetracarbonyl is tetrahedral, iron pentacarbonyl is trigonal bipyramidal, chromium hexacarbonyl is it is octahedral. So based on the geometry, the number of peaks are going to be different for different metal carbonyl system. Now here from this chart, we are just going to understand some shortcuts for predicting the number of peaks. And you know guys, if you have studied any standard book, you will see that maybe we cannot always predict by looking at the structure, but there is a very direct correlation between the number of peaks as well as the point group and the point groups. Alright, this has been observed and laid down in many important books like Miesler and Tarr, like Shriver and Atkins. Alright, you can go through them. So what I've observed is that the local symmetry around the central metal atom of metal carbonyl, they will decide the number and the intensity of the carbonyl stretching bands. All right. For now we are going to talk about the number of stretching bands. ठीक है, तो देखो बहुत सिंपल सी चीज है. We start with the most symmetric system, that is the octahedral system. Okay, so we start firstly from here. What is this? Homoleptic metal carbonyl complex octahedral. ठीक है, कितने number of peak आएंगे? Since all the bonds are same and the geometry everything is same in octahedral, so that's why only one peak I'm going to observe for this. Okay, I move onwards. I have replaced one carbonyl in the axial position with another ligand. Now how many carbonyl bands I'm going to get? See, the point group is different now. First it was octahedral. Now the point group has become C4V. When it is C4V, we have a shortcut. Number of peaks is equals to 4 minus 1 is 3. So for C4V, the number of peaks are always going to be 3 in the case of octahedral, only for octahedral, right? Okay, then I am doing one more ligand replacement. I am putting these two ligands on the axial position, diaxial. ठीक है, तो ये trans हो गया है. Now whenever you are having a trans geometry, whether these two are L or whether these two are carbonyl, they are always going to have one peak for the carbon, because the equatorial all the carbonyls are same. So for trans geometry, peak is always equals to 1, whether it is Ml2CO whole 4 जिसमें कि दो L है और बाकी CO है, or you are having Ml4CO whole 2, then also like this one, last one. Okay, we'll see that once again. Okay, now let's come and replace the other equatorial ligand. I have replaced the equatorial carbonyl with another ligand like this. Now here comes the point group C2V. For C2V, the number of carbonyl is going to give you the number of bands. ये देखो, for C2V point group, the number of carbonyl is going to give you the number of peak. All right. So there are 1, 2, 3, 4 carbonyls in this molecule. That's why 4 peaks. Got it? We move onwards. We are going to replace 3 carbonyl with the ligands. So I have replaced it in a facial manner, as you can see. Again, guys, what is the point group of facial isomer? It is going to be C3V. So for C3V, the number of peaks are always going to be 2. For C3V, it is 3 minus 1 is equals to 2. For C4V, it was 4 minus 1 is equals to 3. This is how it is going to work for the octahedral system. It's like a short trick you can remember. ठीक है? फिर आया meridional isomer. Meridional isomer. I have replaced 3 in a meridional way. Now, what is the point group again? If you try to find out, you will see it is a C2V point group once again. And for C2V, the number of carbonyls, which is 3, is going to be equals to the number of peak. So वो भी 3 है यहाँ पे. All right. Now if I have 4, I have 4 ligands and only 2 carbonyls. Let's say I'm writing a L over here, here and here I'm writing L. So all of these, again, this is going to fall in the trans geometry. I don't need to find out the point group. Trans में कुछ भी हो, when the geometry is trans, peak is only going to be 1. All right. And when the last possibility, and when all of the ligands are, most of the ligands are not carbon, only one carbonyl is left. It is like Ml5CO1. When it is like this, number of peak is going to be 1 only, क्योंकि एक ही तो carbonyl बचा है, right? So this is a short trick by which you can remember the number of peaks of carbonyl in the IR spectrum of metal carbonyl. It is very important, and it has been like in your examination, it has been asked for different geometries. ठीक है, ये octahedral हो गया है. Now we are going to move onwards to tetrahedral complex. ठीक है. So you already know the example of tetrahedral complex. Let's see this one, or any random molecule. See, the metal is surrounded tetrahedrally by the carbonyl. So when you are having all carbonyls, peak is going to be 1 only, right? फिर हमने एक carbonyl को एक ligand से replace कर दिया. Now what? Now there are 3 remaining, but what is the point group? The point group is C3V. The C3V is 3 minus 1, 2. So it is going to give you 2 only. Then we replace one more carbonyl with a ligand. The point group is C2V. C2V के लिए the number of peaks are going to be equal to the number of carbonyls. So 2. Then we have replaced 3 of them and only one carbonyl remains. So एक ही peak आएगा definitely. Now the shortcuts or the tricks are same as octahedral. These tricks are same as octahedral in the case of tetrahedral complex. Alright, आगे चलते हैं. We talk about square planar. Now again, as I told you, when all of the carbonyls are present in a perfect symmetrical system like this, number of peaks are going to be is equals to 1. Okay? When, however, point group changes, कैसे change हुआ? एक ligand लगा दिया in place of one carbonyl. That is going to be C2V. C2V में कितने number of carbonyl है? 1, 2, 3. So the number of carbonyl is equals to the number of peak 3. Then we move onward. I'll just keep 2 ligands on the axial position like this, trans position. Alright, so what is the trans going to be? Always 1. Trans is always 1. And if I put the 2 ligands cis, then it is going to be C2V once again. C2V में क्या होता है? जितने number of carbonyl उतना peak. So that's why it is 2. Then finally we go over to this one where I'm having only one carbonyl and the rest 3 are just ligands. So 1 because there is only one carbonyl left. So here also the same rules are followed. Same rules are followed as in octahedral complexes. Okay. So we are now going to move onwards and see a different geometry. अब देखो यहाँ पे आ गई trigonal bipyramidal geometry. So here in the trigonal bipyramidal system, you know that there are 2 different kinds of parts. If you know this hybridization, you will know that the equatorial ones are made of sp2 hybridized orbitals, and the axial bonds are made of the PD orbitals. Alright, the axial bond. So there is a difference in the orbital composition. That means difference in the bond length, difference in the bond angle, all those things. So because of that, even though we are having all of the ligands is same, it is not going to give us one peak. It is going to give us 2 bands. One is for the equatorial one and the other is for the axial one. Okay. The point group of the simple trigonal bipyramidal system is going to be D3H. Alright, because it has, you can just visualize it like this. It definitely has a C3 axis over here. Plus, along with that, 3 sigma V planes. Alright, or I would write 3 sigma D planes. And along with that, 3 C2 axis. Alright, all many things, and that's why it is pointed to be the D3 point group. D3, D भी हो सकता है, H भी हो सकता है, because there is a sigma plane like this, that's why D3H. ठीक है, तो वो तो बहुत simple है, आपको पता है. So unsubstituted one, D3H, okay, 2 bands because of axial plus equatorial one. Fine. Let's move onwards. Now we are replacing one of the carbonyls with another ligand. मैंने axial वाले को ले लिया, replace कर दिया. What does the point group become now? The point group becomes C3V and it has 3 bands. Alright, now I am putting one more ligand, but this time I am doing it on the equatorial position. So the same ligand that I had on the axial is first going to be put at the equatorial one. Then we will see how many different types of bands are present. 1, 2, 3, 4. It is actually giving you 4 bands. Alright, and C2V is the point group. C2V में क्या होता है? Number of carbonyl is equals to the number of peaks. 4 carbonyl, 4 bands. Now, about this one, MCO3L2. So what is this? I have replaced 2 of the ligands, but from the axial position. Okay, not from the equatorial one. Point group is D3H once again because of the same sigma plane. It is being present, alright, into like this. The molecule is going to be bisected into half and there is a C3 axis plus 3C2. तो ये क्या हो गया, फिर से D3 हो गया, and this sigma plane is the sigma H plane. So here also all of the carbonyls are equatorial, so just one band for them. Okay. MCO3L2 equatorial. Now two of these ligands are going to be cis on equatorial. How is that? Alright, on the equatorial position ये ऐसे ही रह सकते हैं हमेशा. Okay, so now what happens? What is the point group? Just consider rotation like this. So this is going to be a C2V type of point group, and the rotation is going to give you 3 bands because of 1, 2, 3 carbonyls. ठीक है. फिर आता है दूसरा कि इसी लोन पेयर को हमने एक्शियल और इक्वेटोरियल पे रख दिया. ठीक है. फर्स्ट केस I have kept it both on the axial position. Second case both equatorial, and third case both axial and equatorial like this. Okay, so that is going to give you 3 different bands in this way. So guys, we have understood about the carbonyl stretching bands, the number of peaks for different metal carbonyl system of different geometries. Now we are going to move onwards and discuss some interesting examples of the proton NMR spectra for the metal carbonyls. Right, so there have been a lot of questions in the previous years. First we complete the theory and then we are going to discuss those questions. Okay, so yeah, you see proton NMR, for few examples I've taken over here. First one, if you are having a complex like this, what is this? This is a hydrogen bound to iron carbonyl complex like this, and there is a negative charge on this. Alright, so this molecule is basically a carbonylate. Alright, it's an anion. And the proton NMR for this proton is coming at minus 9 ppm. You know that the scale starts from 0, where 0 is the standard for the for these TMS, tetramethylsilane. This is set as a 0. तो इससे भी ज़्यादा shielded है. This proton is very highly shielded. That's why it is like even lesser than 0. Very highly shielded. Alright, why is that so? Because first of all, a proton is definitely or let's say a metal is more electropositive as compared to a proton. So it is going to make the proton shielded. And the second factor is you're having a negative charge on this complex, right? So if you're having a negatively charged complex, the proton inside, which is directly connected to the metal, is absolutely going to be highly shielded. The same is seen over here. Also look at example number B. Now here you have another manganate complex over here, and here the proton which appears is minus 7.5 ppm once again very highly shielded. Alright, so these are some of the examples where metal is directly connected to the proton. I cannot call it a proton because it's not H plus, it is actually H minus over here, it's not H plus. So it's like a hydride, that's why it is so highly shielded. Okay, now let's move onwards and see what are the different types of proton that can be present. Now you can have a hydrocarbon ligand connected to the metal. Now in this particular molecule, if let's say we find out the spectrum, proton NMR spectrum for this particular molecule, we will see that there should be 2 different peaks. One peak is for this hydrogen, which is directly connected to the metal, and you know that it is going to be a negative value because it is very shielded. And the second value is coming for this C5H5. Is it also going to be a negative value? No. Usually what happens is, usually when you consider this system with respect to benzene, you know, it has 6 carbons and 6 electrons. So 6 electron per 6 carbon is going to be like a 1:1 ratio. But there are 6 electrons per 5 carbons. So this is definitely more electron rich than benzene. So benzene का proton NMR value आता है 6.5 से 8.5 depending on the substituent, and regularly it is like 7.8 or something. Now here you see that it is 5 ppm for the CP because metal is there in the lowest oxidation state, it is +1. And it is having carbonyls. It is like metal is not very electron deficient, so it is not going to pull all the electron density from this. And also because of the pi back bonding, it is electron rich, 5 ppm over here. So 2 different values for the protons. Okay, Moving onwards, another example is if the same molecule underwent a particular reaction, which we are going to call as alpha migratory insertion. You will soon know what is alpha migratory insertion when we are talking about the reactions. You see that I have a hydrogen which is very close to this carbonyl. Okay, so what happens now? This hydrogen is going to jump over the carbonyl carbon, and where is the electron density going to go? That electron density is going to go over this metal, and this is going to appear as a acyl group now. All right, so you might have this hydrogen which is doing the alpha migratory insertion, or you might have a methyl. All right, let's say you have a methyl, it can go do an alpha migratory insertion, so it becomes the acyl group. So let's say I'm not writing that this group becomes a ketone or a acyl group. This is going to become an acetyl group like this. After the alpha migratory insertion, it is going to become like this. So this proton and this proton, they are going to have two different values. So there might be a question which is asking you that there's a molecule who is showing two different proton values. One is negative and one is 5 ppm. And after, let's say, heating the molecule, you get two different protons, which is, let's say, because it is connected to an aldehyde, let's say this is going to be very de-shielded, more than 8-9 ppm like that. Okay, and the other one is still 5 ppm. So what is the change in the molecule? There is alpha migratory insertion which has taken place. Okay, just like this. Now in the next example over here, we can still, this molecule can still have a change in the presence of heat that could be like this. All right, so that is the methyl can directly be connected to the metal. It is absolutely going to be more shielded in this case because now it is a methyl ligand. So it is definitely shielded. The protons are negative. Lekin if it is connected to carbonyl, this is an organic moiety and the protons are de-shielded, 2.5 ppm. So there is a difference between this also. Okay, so yes, there are frequent questions which actually come over the proton NMR recorded for these transition reactions. Okay, now let's also see some examples of C13 NMR for the metal carbonyls. Right, so we see over here usually जो C13 NMR आता है metal carbonyls का, since the carbon are shielded, it is going to be minus 40 to 20. It is minus 40 to 20 ppm. Okay, now here you see that metal is in the zero oxidation state. Whenever you form a metal carbonyl, either it is 0 or it is +1. It does not usually go to +2. It's like 0 +1 or -1 it can be, because carbonyl is a pi acceptor and it will favor the formation of a lower oxidation state of the metal. Okay, so when it is so, the carbonyl carbon is definitely electron rich. So one signal in the C13 NMR is going to be obtained for a complete octahedral system. Symmetric octahedral system, only one signal for the C13 NMR because it's a highly symmetric structure. The same happens for the tetrahedral system, only one signal for the carbonyl carbon. Again, it is symmetric. We are a little bit doubtful about the trigonal bipyramidal symmetry because there are axial and equatorial carbonyls. But since all the carbonyls are same, it does not give you two signals in C13. Why? It gave you two signals in the IR, but not over here. Why? Because this one is going to be under the effect of Berry pseudo rotation. It's not just the how many types of carbonyls are there. In the IR, you actually found out the stretching frequency for two different types of carbonyls. So, Berry pseudo rotation, if you know what is Berry pseudo rotation, we have already discussed this, that it is actually going to interconvert between all of these axial and equatorial. It is going to make the same at room temperature. That's why it is only going to give you one signal. All right, but remember, IR does not give you one signal. IR gives you two signals. Okay, for the carbonyl stretching frequency. Remember that, don't forget. Okay, now for the ferrocene, again, we have all of the carbons over here and over here same at room temperature, or only if you are going at very negative temperatures, then only you can like fix the ferrocene into a staggered or a eclipsed conformation. But until you reach that temperature, it is going to be like rotating and giving you only one signal. All carbons are same. Okay. So until and unless it is mentioned that ferrocene, the structure is, or the conformation is locked into staggered or eclipsed, until then everything is same. Then we move onwards to a substituted ferrocene. You see over here, this is a substituted ferrocene. Now, how many number of carbons are present? So you see all of the carbons of this ring are going to be the same, because they are like, this is completely free to rotate. Even though this is also free to rotate, but you can see that there is a sigma plane passing through this molecule as a whole. As a whole, there is a sigma plane in the molecule, and because of that, the upper part of the molecule, this part, is going to have 1, 2 and 3. The 2 and the 3 are going to be the same on this side. Okay, but 1, 2, 3, 4 for this ring, complete ring, only one carbon we will count. Then 5 for this, and the 6 for the methyl. So there will be total 6 signals for the C13 NMR signal. Okay. Now we move onward to another complex. Now this is an iridium based complex over here. C13 NMR signals. So you see that you have another sigma plane which is passing through this part. Alright. And if you keep the hydrogen, like let's say on the plane of paper, you can draw one ammonia below and one ammonia above, and this is on the plane of paper. You can bisect the whole molecule. ठीक है? तो उससे क्या होगा? You will have 1, 2, 3, 4 and 5 different carbons. So this is going to give you 5 signals for the C13 NMR spectrum. ठीक है? So very easy. Now let's do a question. अब ये देखो, एक क्वेश्चन बहुत अच्छा है. The carbonyl resonance in the C13 NMR spectrum of this particular complex shows a triplet at minus 65 degrees centigrade. Now, due to the presence of what? Due to the presence of which of this is correct? It is also given in the question that 103 isotope of rhodium is having an active nuclear spin I value is equals to half, and it is 100% abundant. If it is not 100% abundant, it will have some satellite peaks. We will discuss that also. But here it is 100% abundant. तो क्या होना चाहिए? Try to do this by yourself. Okay. Shows a triplet. Alright, let's think about it. C13 NMR signal. So if you are drawing the structure correctly, for example, in this case, I am giving you the structure. ठीक है कि ये आपका स्ट्रक्चर है. नहीं तो अगर आपको नहीं आता, by chance you don't know how to find the structure. If you know the structure, then only you will be able to like guess it correctly. If you don't know, it will be wrong. तो structure कैसे निकालोगे? First of all, you are going to find the metal-metal bond. Yes, isn't it? Because there are 3 rhodiums in it. So count the number of electrons. 5 electrons from Cp, 9 from rhodium, and एक ही carbonyl है तो 2 ले लो. It's going to be 11 plus 5, 16. 16 electrons. So 3 metal है, 16 electrons. So how many metal bond per metal? There should be 2. अगर ये rhodium है, इसके पास 16 electrons है, after counting from the ligands, then there must be like 2 metal bonds per metal. इतना आपको समझ में आ गया. You have practiced a lot of questions on that. Right, this is how the geometry is. Each rhodium has 1 carbonyl and 1 Cp. 1 carbonyl, 1 Cp. 1 carbonyl and 1 Cp. So for example, this is where you got it. Now the questioner is not asking you if the carbonyl carbon is going to be, if the carbonyl carbon is going to be like bridging or not. ये तो directly नहीं पूछा है, indirectly पूछा है. देखो. So carbonyl resonance shows a triplet. So let's see, if I say that the carbonyl is terminal, then what will happen? This carbonyl carbon is going to be affected by the nuclear spin of this rhodium, because this is directly connected. It is going to split it. कैसे split करेगा? 2ni plus 1 rule से split करेगा. So 2 into n is basically 1 rhodium it is connected to. The value is half plus 1. So this is what? 1 plus 1 2, it is going to only be a doublet. अगर ये structure सही होता, if this was the correct structure, then the signal should have been a doublet. Okay, and it is specifically mentioning only carbonyl resonance, it's not talking about the CP, right? तो ये structure सही नहीं है. What minor change can we do? The minor change that we can do is bridging. We can do the bridging of the carbonyl. Let's see, because the number of electron will remain the same. तो bridging कर दिया हमने, fine. Now this carbonyl carbon is actually connected to 2 rhodiums over here. That means कि ये जो carbonyl carbon है, that is going to be split by 2ni plus 1 rule again. Now this time I'm writing n is equals to 2 because it's connected to 2 rhodium. तो ये cancel out होके आता है 3. Now it's going to be a triplet. So this carbonyl carbon is only going to be split by the metal, because this is the CP electrons are very far away, and also they are not sigma bonded, they are pi bonded. So उसका कोई effect नहीं होगा. So it is triplet because of a mu2 bridging carbonyl. Terminal carbonyl से it is only going to be a doublet. Mu3 bridging not possible. This is all wrong. So mu2 bridging carbonyl is the correct answer. How nice. So this is our wrong structure. This is our right structure. Now next, we also have some questions from the 31p NMR spectrum. ठीक है, कैसा है देखो. So first of all, we are going to talk about the Wilkinson's catalyst, because obviously we find a phosphine over there. जहाँ जहाँ phosphine है वहीं पे ये question आता है. तो इसका स्ट्रक्चर देख लेते हैं. दिस इज आवर विल्किंसन्स कैटलिस्ट. ऑलराइट, सो इफ वी ट्राई टू प्रैक्टिस how we are going to get signals, you will be eventually able to do it in question. तो पहले इसका प्रैक्टिस कर लेते हैं हम. That is already you know that for rhodium 103, in the last question you saw this, I value is going to be equals to half, Okay, just try to remember as many examples as possible. अभी आपको पता चल गया rhodium active है, तो examiner के लिए wait मत करना कि वो बताएगा rhodium active है. Just remember rhodium is active. Okay, so yeah. Now, do you see a sigma plane over here? Yes, we do. This is a sigma plane. Now, how many types of phosphorus are present? There are 2 types. This is, let's say, AA, and this is, let's say, B. So there will be 2 different signals, right? Now these signals, these phosphorus are going to split each other because there is only a difference of 1 atom. What is this? 2J coupling. So 2J coupling किसकी हो रही है? Phosphorus PA-PB की हो रही है. As well as rhodium and phosphorus coupling is also taking place. So that because of that also it is going to split. तो चलो signal देखते हैं. Since it is directly connected to rhodium, first the rhodium will split. I am talking about PA signal. PA मतलब कि the signal of the A phosphorus. It is going to be split into a doublet by rhodium first. Then it is going to be split into another doublet by PB. क्योंकि PB एक ही है, only one PB is present, that's why. 2Ni plus 1, you try it out. It will be a doublet only. So what does it give you? It gives you doublet of a doublet, and the intensity is going to be 1 1 1 1. Why? Because it's not a quartet or anything. ये क्या है? Doublet of doublet है. थोड़ा space लेके दोनों same मिलेगा. So this is doublet of doublet for PA. ठीक है? Now we try out the PB. For PB, how it's going to be? You are going to split the PB into a doublet by rhodium. ठीक है? No problem. But there are 2 PA. 2 है PA. तो कैसे split करेंगे? By the 2Ni plus 1. As I told you already, just make it a shortcut, N plus 1 rule. तो मतलब कि there are, when the I value is half, then the 2 in the half cuts off and you have the N plus 1, right? So it's going to be 2 plus 1, 3. Right? So it's just going to be a triplet with 1:2:1 intensity. Like this. This is going to be because of PA. तो ये क्या हो गया है? 1 triplet, another triplet. So what is this? A triplet of doublet या doublet of triplet, like that. ठीक है? So it's actually a doublet of triplet. So I should write doublet of triplet because this was a doublet और वो double हो गया है, इसलिए doublet of triplet है ये. Okay, so this is what you have. 2 signals different. This is because of the PB. It is splitting like this. Similarly, let's look for this one. Now in this molecule, it's very similar to Vasca's complex, but यहाँ पे एक chlorine नहीं है. So what happens is you are having a bisphosphine over here. How many different phosphine atoms are present? How many phosphorus are present? 1, 2 and 3 phosphorus and 4 phosphorus actually. Yeah, there are actually 4 phosphorus atoms present, लेकिन क्योंकि एक sigma plane है यहाँ पे भी. So I'll write PA, PB and PC like this. So how are they going to split? First of all, the PA are going to be giving you one peak. PB gives you another peak. Iridium is not going to make it split. अभी यहाँ बताया नहीं है, iridium को हम inactive consider करेंगे. So we are not splitting it. So PC you're getting a singlet because it's very far away from PB. And here I might get a doublet because of the, yes, I think PC is going to be a singlet because this is very far away from here, and this PB is going to be split into a triplet because of PA not taking the contribution of iridium, and PA is going to be split into a doublet because of PB. So yeah, this is how it is going to appear. It's not all singlet, okay? Yes. चलो एक सिंगलेट रहने देते हैं, एक ट्रिपलेट हो जाएगा और एक हो जाएगा डबलेट, like this. Okay, who is going to be doublet? The PA is going to be doublet because of PB, and PB is going to be a triplet, and the PC is going to be a singlet. That's it. Very simple. आगे चलते हैं. Now look at this. Some questions we are going to try out. On the basis of the given information on the carbonyl band, which ligand among the following pair of complexes, carbonyl or selenocarbonyl, this is a nitrosyl and this is a sulfur thionitrosyl, is a better pi acceptor ligand? Explain briefly. So this is a question from the back question from the BD Gupta exercise. It's very nice. ये आपको बस इतना ही पूछ रहा है that based on the given data, which is a better pi acceptor in the first one and in the second one. Alright, just try to understand the question and I'll answer. Alright, so it is very evident that the higher frequency, see what is happening over here, the rhenium complex is basically like this. You are having a eta 5 CP connected to the rhenium like this, and the rest of the 3 are carbonyls in this way. Alright, so whether you are having a carbonyl or you are having one carbonyl replaced by a selenocarbonyl like this, CSE and CO and CO again. So what is the difference that this is going to make? Let's compare. Alright, what is the difference when this is replaced by this? Difference in whom? The stretching frequencies of these carbonyls. There are 2 and that's why you're getting the 2 value over here. Alright, so what do you have? You are having the, see, for all carbonyls, the value is a little bit lower as compared to we are having CSE. A value is a little bit higher. What do you mean by that? इसकी value high क्यों हो गई है? Because selenocarbonyl is maybe a better pi acceptor. If CSE is a better pi acceptor, if it is a better pi acceptor, then what will happen? Then the electron density that is coming from here, because the negative ligand, like, so that is going to be coming to the rhenium, and rhenium is going to pass out this electron density more to this better pi acceptor as compared to the carbonyls, and because of that the carbonyl stretching frequency increases. So that has exactly happened over here. So this CSE is a better pi acceptor as compared to the carbonyl. Okay, the next example over here, first one is done. दूसरे में देखते हैं. देखो यहाँ value दी हुई है, but in the exam the value will not be given. Maybe they are just directly asking you, not giving the value. So that's why it is important to practice as many such questions. You are once having a nitrosyl which is having a 2028-1955 centimeter inverse value, and only a slight difference when you are having the NS. Only a slight difference. What is the difference? 20331962. So what is the value? A little bit higher. A little bit higher value. So once again, when do you see the higher value? When you are having a better pi acceptor, then only you see the bond order is going to increase, and that's why the value is higher as compared to this. Okay, इसका मतलब क्या है? NS is again a better pi acceptor than NO. All right. So this is it. Very simple, just based on the stretching frequencies you had to say. Now we move onwards and do another question. When a compound A is heated, CO gas is driven off. The product B so formed readily reacts with carbonyl and reverses the reaction. Infrared spectral studies indicate that the carbonyl stretching frequency value of A at 1960 and B at 1850 centimeter inverse. You have to draw the structure of A and B. These are the most interesting questions that you have. Alright, structure determination question types are the most interesting. So what are we waiting for? Chalo, try it on your own and then I'll be answering. And let me tell you that this question has also appeared in your CSIRNET examination. The same reaction was given. No, this molecule was given that this molecule in the presence of heat is going to dry off two molecules of carbon monoxide, and in result it undergoes a change in bond order. What is the change in bond order? The change in bond order वो हम calculate करते हैं यहाँ से. ठीक है, so first of all we try to understand the structure by the electron calculation. So what is this? 5 electrons from the CP. molybdenum में आएगा 6 electron, chromium के group में है, then 2 into 3 is again 6 whole multiplied by 2. So what is this going to be? 6 6 12, sorry, yeah, 12 plus 5 17. So you know, आपको total metal metal bond calculate करने की जरूरत नहीं है. You know by looking at this number that there is one metal metal bond which is going to be short. Okay, one metal metal bond. Okay. Now in this one, after the removal of two carbonyl gas, it is going to be 5 plus 6 plus 4 whole multiplied by 2. That is 15 into 2. 15 means 3 electrons short from 18. तो कितने metal metal bond है? There is going to be 3 molybdenum bond. So what is the change in bond order? molybdenum bond एक था, 1 से 3 change हुआ है. That was the previous year question. Now we see the structure. What is possible? Molybdenum is kind of big in size, so I don't think that carbonyl is going to be bridging. ठीक है, so we naturally draw the carbonyl. Each molybdenum has a CP. Let's try to draw them opposite because they are bulky. So there are going to be 3 carbonyls, another 3 carbonyls like this in this way. Or even if you want to, let's say, do a bridging thing, it could go like this. But we can't confirm the bridging without the spectral studies, isn't it? 1 2 3 4 5 6. Yeah. Either it could be this or it could be this, like that. But after the removal of this carbonyl, it definitely has to be a molybdenum triple bond. And here what is left? You are only having 2 carbonyl per molybdenum. That means either you can write the structure like this. अच्छा, ये पहले कितने थे? 1 2 3. Okay, now there are 2. So either it is going to be like this, or maybe because they are closer, they are going to be doing some bridging. दोनों structure possible है. Both the structures are possible. We are going to say based on the IR. Now the product B so formed readily reacts with carbonyl and reverses the reaction. Infrared spectral studies value of A show this much. मतलब A के अंदर क्या है? 1960 centimeter inverse. That means it is terminal. It is going to be terminal. So what is the correct structure? This first one is going to be the correct structure, right? Because all of the carbonyls are going to be terminal. This is correct. 1960 centimeter inverse. And B at 1850. So for B, I can say that there is a bridging carbonyl which is present. So it is possible that you are having a bridging carbonyl क्योंकि अभी molybdenum दोनों पास में आ गए हैं, okay, because of the shorter bond. So either it could be like this, or it could also be like this, since there are only one type of carbonyls. So it could also be doing one more bridging in this way. This can also be correct, okay. So B is going to be like this. All right. And you know what, if you want me to write it like more beautifully, in a more beautiful manner, just like it's written in the book, so that you can be impressed, then I can write this molecule like this. But you know, both of these are bridged. आप उसको कितना भी सुंदर बना के लिखो, both of these are bridged. In this way we can write this molecule, both of these are same. Why am I so sure? Because see, the value is only one value given means all of these are bridging. अगर दो value होती तो some bridging, some not bridging, I can say that, but for B all of these are bridging and this is the correct structure, not this one. Okay,